Sometimes, rather than making a solution fresh by dissolving a solid in water, we want to do it by dilution. Dilution is taking an already made solution and adding water to it to make it more dilute. In other words, less concentrated. The reason why we want to do it this way is that concentrated solutions are much cheaper and easier to store and to ship. We can take a concentrated solution and dilute it later to get the concentration we actually need. Calculations related to dilution depend on the fact that the number of moles of the solute will remain unchanged by adding in solvents such as water. The moles of the solute before the dilution equal the moles of the solute after the dilution. If we look at the graduated cylinders in the picture, the one on the left is our starting concentration of copper nitrate solution. It's a darker blue, and there's a smaller volume of it. When we add water to it, the copper nitrate solution gets diluted. The color of the copper nitrate solution becomes a lighter blue, and the volume is getting larger because we've added some water to it. But the number of moles of the copper nitrate is not changing between those two pictures. It's the same in both. All we've done is mess with the water. We haven't done anything to change the number of moles of the copper nitrate. Sometimes we abbreviate moles as N, like number of moles. N1 moles of solute before the dilution equals N2 moles of solute after the dilution. We can also abbreviate our rearrangement of our molarity equation. Moles equals molarity times liters. We could write this as N equals ml. This equation is going to be true for a variety of different circumstances. Moles equals molarity times liters in circumstance number 1, so N1 equals M1 times L1. Moles equals molarity times liters in circumstance number 2, so N2 equals M2 times L2. We know that the number of moles before the dilution equals the number of moles after the dilution. N1 equals N2. We can set those equal to each other, and therefore we can set the other things on the other side of the equal sign equal to each other. Because N1 equals N2, M1L1 equals M2L2. We can generalize this equation as C1V1 equals C2V2, where C stands for concentration and V stands for volume. Concentration times volume before the dilution equals concentration times volume after the dilution. We can do this for any variety of units of concentration and any variety of units of volume, as long as they're the same on both sides. Remember that in the 3 rearrangements of the molarity equation, volume has to be in liters. In this before and after equation for dilution, volume could be in any unit you want, such as milliliters, as long as the units are the same on both sides. That's because of simple algebraic rules. If we multiply both sides of an equation by some number, or divide both sides of an equation by some number, that equation is still valid. Let's say we were multiplying both sides by 1,000, going from liters to milliliters. Then the equation is still valid. Here's an example. Using our dilution equation, we're given a starting concentration and a starting volume. Our starting concentration is 5 molar, and our starting volume is 0.850 liters. We're told that it's diluted to a volume of 1.80 liters. So that's our new volume, V2. We can identify our variables. C1, the initial concentration, is 5 molar. V1 is 0.850 liters, and V2 is 1.80 liters. We're using our dilution equation, C1V1 equals C2V2. But in order to use this equation, we need to get the variable that we're trying to solve for by itself on one side of the equal sign. In this case, our missing variable is C2. So we need to get C2, the new concentration, by itself. To do that, we divide both sides by V2. We get C2 equals C1 times V1 divided by V2. and then we can plug in our numbers that we identified. The C1 and the V1 go on the top, and the V2 goes on the bottom. We do 5 molar times 0.850 liters divided by 1.80 liters, and we come out with 2.36 molar as our concentration. With our dilutions, the result should make sense. If we're starting with a concentration of 5 molar and we're diluting it, it's getting weaker. So we should expect to get a smaller molarity for our new concentration. In fact, we do. We get 2.36 molar. What volume of 1.59 molar potassium hydroxide is required to prepare 5 liters of 0.100 molar potassium hydroxide? Pay attention to the wording here for your ones and your twos. The ones is the before set of conditions before it's diluted. The twos are your new sets of conditions after it's diluted. Is the answer A, 314 milliliters, B, 795 milliliters, C, 3.18 milliliters, or D, 3,180 milliliters? The correct answer is A, 314 milliliters. In this problem, C1, the initial concentration, is 1.59 molar. V1 is actually what we are trying to find. We want to know how much of our initial solution to use. This is also a very common type of calculation to encounter in research. C2, the concentration of the diluted solution, is 0.100 molar, and V2, the volume of the diluted solution, is 5.00 liters. After rearranging the dilution equation to solve for initial volume, you get V1 equals C2V2 divided by C1. You plug in your numbers and get 0.314, and the units on that will be liters, since your V2 is in liters. Remember, the units have to be consistent. Try crossing off units like you would in a conversion factor problem, and you'll see why we get liters. Since all the answer choices are in milliliters, you convert to milliliters by dividing by 10 to the minus 3 and come out with 314 milliliters. You have to be very careful with the wording on your dilution problems. Sometimes it will tell us the amount of liquid that's the final volume, or sometimes it will tell us how much liquid is added to the amount that's already there. Here's an example of the latter. We have 45 milliliters of water being added to a solution. The solution that's already there is 250 milliliters of a 0.75 molar solution. We're still using our equation C1V1 equals C2V2, but we have to be very careful about what we're putting in as that V2. C1, our initial concentration, is 0.75 molar. Our V1 is going to be the 250 milliliters that it started out as, and the V2 ends up being a total of 295 milliliters, the 250 that we started out with, plus the 45 that we added. Then we're going to solve for the molarity of the diluted solution. That's going to be C2 that we're trying to solve for. Our rearrangement of the dilution equation that gets C2 by itself on one side of the equal sign is C2 equals C1V1 divided by V2. We can plug in all our variables and solve to come out with 0.64 molar as the molarity of the diluted solution.